Hello and welcome back to Calculus 2 on this chilly Saturday morning. I should actually start and open with the weather, to add more value to the stream. Good morning. It is exactly, they say the date and the time, even though you can see it right here. And then, say it's 52 degrees, and tell about the humidity, the wind, and everything else, and then just ease into numerical integration. So, direct segue into. So, what are we going to do today? We are going to continue what you guys learned in Chapter 5, Calc 1. You learned in 5.1 that you can approximate area under the curve by dividing the area under the curve into rectangles, and then using those rectangles to approximate. So this is what you did. This is, I'll label this as old stuff. How about that? Old stuff. So you took some kind of a function. In this case, we can say square root of x. And let's say you want to calculate area from 2 to 5. Let's go 2 to 6. So we'll go 2 to 6. And you have square root of x as a function. And what you did is you used either the left hand sums or the right hand sums, and the left hand and right hand only, what it does, it says we're going to create a rectangle using the left point or the right point. So which one do you want? Because they are the same in some sense. So should we do left or right? Left, okay. So that's going to be this red. If we're going to do the left, we're going to go to the left corner and just draw these flat rectangles. That creates error because the area, in this case, the area we calculate is going to be less than what the actual area is. So we are going to have, in this case, 4 rectangles. All right, we're going to have 4 rectangles here. And when you calculate their area, you see first that you have the delta, we call this delta x, each one of these lengths. In this case, they're all the same width. And the formula that we use for delta x is b minus a over n. And for us, a and b are the numbers that are the interval for our integration. We also use values x0, x1, x2, x3, and x4 in this case to denote the x values that we'll be using to calculate. So now, to calculate area, so area will be approximated by delta x, which is the width, times the height, which is f of 2. So f of 2 is the height. That's where the red dot is. That's the height of the rectangle, f of 2. And then the width of the rectangle is delta x. So delta x times the height gives us area of the first, plus delta x times f of 3, plus delta x times f of 4, plus delta x f of 5. So this is what you did in Calc 1. And then you plug everything in. That's 1 times square root of 2, plus 1 times square root of 3, plus 1 times square root of 4, plus 1 times square root of 5. So that's your calculation because the function, it was square root of x. Now that is usually going to be something that you can't compute by hand, obviously, but in this case, root x, so we can integrate that. And when you calculate this, you get 1.4 plus 1.7 plus 2 plus 2.2. And then you add all of these, so 2, 4, 6, 7, 3. So we calculate that the area is approximately 7.3. And that's what you did in Calc 1. Now you could have used the right sums, and if you use the right sums, obviously it is going to overshoot the area. So true area is more than 7.3. But we are approximating, so 7.3 is the equation. Okay, so that's that part. So now we are going to learn 3 formulas that will improve on this approximation, because remember that I have a lot of error over here. So I'm just going to do this. No, we're not gonna, no, it will be different methods, so it's not gonna produce as much error. So we had error here, and what we are going to do now, we're going to position these things differently so that we can okay, so the first one is going to be called Midpoint Rule. Midpoint Rule. We're going to draw the same, let's say square root of x, doesn't matter. And now I'm going to, so 1, 2, 3, 4, so 1, 2, 3, 4, 5, and 6. We still have our delta x the same, which is b minus a over n. N is the number of rectangles. If you are a computer science major, you should be programming this at home, and you should ask for the input, right, for the number of rectangles. So n should be something that the user decides on. 10,000, 100,000, Anyway, so what am I going to do now? Let me zoom in on the first. I need you to look, and then you can catch up writing later. So these are the same 4 divisions that we had before. Now, I'm zooming onto the first rectangle because I want to show the new configuration. Look, if you use what we used earlier, which are the left rectangles, you'd see that that's one-sided, and you have a lot of error here. All right. If you use the right, then it would look like this, and you would have a lot of error there. So both of these cases are in some way extreme, and they create error. Now, instead of having these, what we do is we create from the bottom up, right? You draw the middle line, and the middle line is going to hit the function somewhere, and that's where you draw the straight line for the rectangle. You see what happens? You create extra error here, but then you undershoot on this side. They don't cancel exactly, but they roughly cancel, making this method vastly superior to the previous two. So it's a really clever thing, the way it's designed. So if you, from the midpoint, if you extend the line upward and you hit the curve, then you overshoot on one side, you undershoot on the other side, and then they roughly cancel. They don't cancel completely, but they give a very nice approximation. So now, when we zoom back to our standard size over here, we see that we can draw these midlines Oh, come on. We can draw these midlines everywhere and then use midlines to create rectangles. And these will have less error than what we... So now, there's never free lunch, right? So because there is never free lunch, right, we have 2.5, 3.5, 4.5, and 5.5 to compute that rather than at integers in this case. But that's okay, I mean. So now what do we have? If we are talking theory, we have x0, x1, and so on. Those are the x2, x3, and x4. Those are the black points. And if I want to come up with a formula, what the area is approximated by, I see that I have delta x times the function computed at the average of the 2 points. So I have 2 plus 3 is 5 divided by 2 is 2.5. That's where I compute the height. Plus delta x f of x0 plus, x1 plus x2 over 2 plus delta x times f of x2 plus x3 over 2 plus ... going forever. So this is going to create the midpoint formula, which is the one you are memorizing. So we'll call this Mn for midpoint, n for number of rectangles you're going to use. And we're going to factor out delta x and just have f of x0 plus x1 over 2 plus f of x1 plus x2 over 2 plus f of x2 plus x3 over 2 plus ... to get to the, well, let's put the last term in because we can, right? Plus f of xn minus 1 plus xn over 2. So that's the last term, the one that has xn. This, well, we'll put the cloud on it, right? This is your midpoint formula, Mn. That's the midpoint formula. And the way it goes is you calculate the midpoints, and then you calculate the function at those midpoints times delta x and so on. So if we are to do the problem above, we start by calculating delta x. Delta x is going to be 6 minus 2 divided by 4 because I have 4 rectangles. That's 4 over 4, which gives me 1. So now, if I draw my partition, I know I have to start at 2. Then the next is 3 because it's the next one. Then the 4, then the 5, and then we end at 6. So these are my x0, x1, x2, x3, and x4, knowing that the last one are a and b, which are our interval. Because you have delta x in between each one of these, right? Going over. So now I have my delta x's. And if I'm using my formula, in this case, I will say area is approximated by M4. Right? M stands for a midpoint, and the 4 stands for 4 rectangles. And we are just plugging delta x is 1. The function is the square root. So I have square root of 2.5 plus the square root of 3.5 plus the square root of 4.5 plus the square root of 5.5, because I have to calculate the function at the midpoints. And the midpoints, well, I didn't write them here. I should have 2.5, 3.5, 4.5, and 5.5. So you have to calculate all of the midpoints. And you have 4 rectangles, you have 4 midpoints. So you calculate each one of those. And this will give you the much better answer than what you had before. We had the 7.3. We know that was less than what it should be. So now we're just going to have the square root of 2.5 plus the square root of 3.5. Oops. Plus the square root of 4.5. And finally, plus the square root of 5.5. And that should give us 7.9. So now area is approximated to be 7.9. Last time we got 7.3, and we know that we were under because there was a lot of error on those first 2 rectangles at least. Now we have the midpoint calculation, which is better. So as you can see, it's just multiplication and addition, right? To solve these problems. So to approximate the area under the curve using the midpoint rule, you will be calculating the midpoint of every delta x, and you will calculate the function at that value. So that's midpoint. The next one is trapezoid.
I have a question.
Yes.
How come we're learning the midpoint if we already know how to get the exact area under a curve?
Can't integrate.
Okay.
So you have to program. There are integrals, there are functions that cannot be integrated. One of the rules we learned for integration by parts is that when you pick your u and dv, you focus more on dv than on u, because dv is going to get integrated and you can't integrate everything, or some things are absolutely terrible to integrate, right? So you pick, and then you say everything can be differentiated, right? So now we are learning these rules because there are functions upon functions, infinitely many of them, that cannot be integrated at all. And we use these numerical methods. Also, this is how computers solve definite integrals. Even though if it's x squared, it's going to use this, because the computer doesn't know, right? To say, oh, it's x cubed over 3, and unless someone programs it, right? So even if you are to hard code that the integral of x squared is x cubed over 3, and then computer knows, right?
Choose a ridiculous number for n.
Yeah, you just go up to 793, and maybe you didn't get into your code to hard code that, okay? So, or even if you code you code the formula, then I add an additional x or put something else, the computer can't do it, right? So it's much easier to not mess with any of the formulas ever in coding. You just code this. And it solves 100% of the integrals, even those that can't be integrated and those that can, and you don't have to worry about exponents and the size and all these kind of things, right? So we use this a lot in later mathematics, right? There are whole courses on numerical approximation and numerical and asymptotics and so on. So there's a lot of this stuff coming up. Level of math is obviously 300, 400, and then graduate level will have a lot of these things. The next one is trapezoid rule, and the title obviously gives it away. We are going to create trapezoids rather than rectangles. And this one now, so we'll again start with the picture, we'll zoom in, we'll zoom out, and write the formula, and that will be it. So we start with our square root. I'm going to go with the same 2 to, keep everything same. So 1, 2, 3, 4, 5, 6. Keep the same function, keep the same interval so we can see it. All right, so for trapezoid now, you are going to connect these endpoints with straight lines. You know they're curves, which is why the black and red over here is still not 100% on top of each other. You can see the black kind of poking out, curving behind the red, right? So now what I'm going to do is I'm going to take this first rectangle here, well, trapezoid, and just flip it on its side. Nope, the other way. So this is where x equals 2, x equals 3, and this is f of 2. Actually, you know what? I have to write these as lengths. So this is delta x length, that's delta x length. Then this over here is f of 2 length, which is f of 2 is the shorter one. And this is f of 3, which is the longer one. There we go. So you see, and maybe I should exaggerate more so we know it's a trapezoid. There we go. Now, if you remember, for trapezoid, the way they label is A, B, and the height. And the area of the single trapezoid is A plus B over 2 times the height. A plus B over 2 times the height. So that's the area for the trapezoid. Now, if we translate that into our language, area of this one trapezoid would be f of 2 plus f of 3 divided by 2 delta x, because those are the values we are using in this case. So now, if I label the values x0, x1, x2, x3, x4, and you can go on as far as you have to, we can approximate the area by what? Well, I have delta x times, that's the height, times, and now I have f of x0 plus f of x1 divided by 2. So that will be the first trapezoid, I have the two parallel sides, right? That's f of 2 and f of 3. So I'm going to call them f of x0 and f of x1 because they don't have to be 2 and 3. It can be whatever numbers need to be. So I have the first two x values, calculate the function of them to get those lengths, and then average them times the height, and the height is now delta x, which is the width actually, because you flip the. Generally, trapezoids are drawn this way, right? And we have a, b, and the height h. Well, it's okay if one side is flat. That's okay for the trapezoid. Anyway, so that's the first one, plus delta x f of x1 plus f of x2 divided by 2 plus dot, dot, dot. So what you see here is the pattern now. You see the pattern where you always average the functions and then times delta x. So to create the formula, this is the formula we are memorizing. Area for the trapezoid, so Tn, trapezoid rule with n rectangles. You can have 4 rectangles, you can have 100, you can have 1,000, depending on what you code in. Or you can use user input, that's the best. So we have delta x over 2 is going to be kicked outside. So when you take delta x over 2, look what's left. F of x0 plus f of x1 plus another f of x1, f of x2, there will be another f of x2, and so on. So we have just f of x0 plus 2 f of x1 plus 2 f of x2 plus dot, dot, dot plus f of x2, f of xn minus 1, that's the second to last, and the last term is just f of xn. The last one is single as well. And that's our trapezoid rule. Yes?
Oh, were you getting the
2 in front of x1 and
yeah.
you see there are 2 of them? 1, 2.
Oh, no.
So the next term would be x2, x3. So x2 and the x2 there. So only the first and the last are, and this x0 is always a, and the xn, which is the last one, is always your b. So technically f of a is a single and f of b a single, and all of the ones in the middle are always double from the formula. So the pattern that you memorize here is 1, 2, 2, 2, 2, 2, 2, 2, 1 at the end. Right? That's the pattern you're memorizing. You memorize the pattern of these coefficients. So if you want to compute our problem from before with the square root, we calculate our delta x, which is 6 minus 2 divided by 4, which is again 1. We have our partition again, that it's 2, 3, 4, 5, and 6. So we have our partition, and those are my x0, x1, x2, x3, x4, and I just plug them in the formula. So area is approximated by T4, trapezoid rule with 4 rectangles, and that's going to be delta x is 1, so 1/2, and I just go and I plug in square root of 2, square root of 2 plus 2 square root of 3 plus 2 square root of 4 plus 2 square root of 5 plus square root of 6 single. So the first and the last are single, and all of the other ones in the middle are doubles. When you punch this in the calculator, you better get something around 7.9, right? Because we know that the midpoint gave us 7.9, so this one better be 7.9. So we have 0.5 times open parenthesis. We have a square root of 2 plus 2 times square root of 3 plus 2 times square root of 4, that's just 4, plus 2 times square root of 5, and plus a single square root of 6. And we get 7.899999. 7.89997, right, which is again 7.9, right, like last time. So we got 7.9 with, you should always keep one extra decimal, guys. This is terrible to leave it like this because your input data were all integers, right? So if you learned anything from chemistry or physics or these STEM courses, when you do the calculation, you are allowed to present an extra decimal. So if your input numbers have 2 decimals, your answer is allowed to have 3, and that's it. You cannot provide 17 decimals because think about adding the error and precision and being really, arrogant in that way. If your measurement can only provide integers, and now what? Your calculation. So you have a scale that can only measure grams. It cannot measure 0.5 of a gram or something like that. But your calculation provided, 17 decimals to the, like really? So this answer should be 7.9. And the reason why I have the decimal I have over there is to show that it's, the calculation will give you something that would round. So it's not exact. These are all approximations. These are not exact. And even if you are to do integrate, you would still have approximate answer because once you go into decimals from square root of 2 and square root of 3 and so on, you will be calculating square root of 6 and a square root of 2 in your exact answer anyway, if you integrate. So it's never exact unless you leave it as a root 6 in the answer. So now we have reviewed Calc 1. We reviewed left-hand side calculation, which is the same as the right point calculation. We learned the midpoint rule, and we learned the trapezoid rule. One more, and that one is called Simpsons rule, and that one fits parabolas under the curve. So Simpsons rule. Same story. We are going to draw our square root of x function and go 2 to 6 again. Actually, before we do this, let me write in blood, which means very important, right? Next to Simpsons rule, n must be even. And I'll scream 3 times. N must be even. Otherwise, method doesn't work. So, on a test, if I ask to calculate the Simpsons rule with 7 rectangles, right? And you go do it, I get to write the noob. All right, good. So we have 1, 2, 3, 4, 5, and 6 over here. So these are my levels. And what I'm going to do is I'm going to take now approximation goes like this. You pick 3 points and you fit the piece of parabola through it. Now, this one is harder to derive, so we're not going to do the proof for this one like we derived the last ones. I'll just tell you how you get this. And then I'm not sure even if they did in a book. If you're interested in a proof, definitely we can talk about it. Then you pick the next 3 points, you fit the parabola through it. Then you pick the next 3 points and you fit parabola through. And what you see is that the more you start fitting these, right, they kind of stack up, start stacking up. So the next one we don't have anymore, so we're going to stop. And we actually have 4, 1, 2, 3, 4, so that's even, it's good, right? But there will be a next one and the next one and the next one. So we have 10,000 of these, right? 10,000 is even. There's going to be a lot of them. And the way that you figure this out is you have to fit the parabola through the 3 points. So if you know, it's not studied in algebra. When pre-calculus was a stronger pre-calculus, then we used to teach that to students on how to fit the parabola to 3 points. You have, for parabola, I'm just going to outline it, and then if you care about it, you can do it at home. ax squared plus bx plus c, right? So that's the parabola. And what you do is you say, oh, I am going to fit the parabola through points 2, 3, and 4. So you will have a2 squared plus b2 plus c, and then that one gives you 4, well, equals 0, right? That gives you 4a plus 2b plus c equals to 4. And then similarly, you have to also fit this one through x equals 3. So you have a3 squared plus b times 3 plus c equals 0. So that gives you 9a plus 3b plus c equals to 0. And then you also have to fit through 4. So a4 squared plus b times 4 plus c equal to 0. And you get 16a plus 4b plus c equals 0. And what you see over there is you have a system of 3 equations and 3 unknowns. You solve that system and you will get a, b, and c in terms of, but you have to do it in terms of x0, x1, and x2, not in terms of 2, 3, and 4, because it's a particular example. I just use this to explain the process of deriving it. So it's about an hour of work to shovel through the algebra, especially when you don't have numbers. You have x0s and x1s, and So generally we don't bother students with that kind of stuff, but that's the way to, I forgot to put equal 0 here, there we go. So this is the general form, right? And then you have to compute at x0, so you put x0 everywhere, and that gives you the first equation that would actually have x0 and x0 squared, x0, then x1 squared, then x1, and x2 squared. And you have to solve the system in terms of those. So after an hour of algebra, right, it all boils down to area is approximated by Sn, which is delta x over 3. And now you get f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus 2 f of x2 plus ... plus 2 f of xn minus 2 plus 4 f of xn minus 1 plus f of xn, and then it's done. Now you will say, do you really have to write 15,000 terms in the formula? Yes, I have. I have to, because you have to see the pattern. And what's the pattern?
4, 2, 4, 2, 4, 2, and it ends with, oh, well, after the...
So 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1.
Right.
So it goes 1, 4, 2, 2, 4, 1. Right? 1, 4, 2, 2, 4, 1, right? So let me just put over here in purple. patterns. We have the midpoint pattern, 1, 1, 1, 1, 1. Then I have the trapezoid pattern, 1, 2, 2, 2, 2, 2, 1. And then I have Simpson pattern, 1, 4, 2, 4, 2, 4, dot, 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 2, 4, 1. So these are your patterns for midpoint, trapezoid, and Simpson. So you are memorizing these formulas, memorizing these patterns, and then no matter what is given to you, it doesn't matter if you can integrate, you can't integrate, you have no clue how to integrate, you should be able to compute the function at the point that was given, utilizing any of these formulas. So now let's use this Simpson formula to calculate. Oh, by the way, if you use the Simpson formula on a parabola, let's say your problem was 3x squared minus 7x plus 17. You will get exact answer. You will get exact answer if you use Simpson's rule on the parabola, because Simpson's rule is quadratic approximation. Right? Simpson's rule is quadratic approximation, and that's the it's a quadratic problem, so therefore it has to give you exact answer if you use Simpson's rule there, which is really cool.
Have at least 4 points for Simpson's rule.
Yes. So 4, 4, 6, 8, yes. The 4 points will give you 1, 4, 4, 1 pattern. The other one will give you 1, 4, 2, 2, 4, 1 pattern, right? So every time you will be adding stuff in the middle. So if we are to work out our problem from before, delta x is again 6 minus 2 over 4, which is still 1. The partitioning is still the same, 2, 3, 4, 5, and 6. So those are your x0, x1, x2, x3, x4. And now area approximated by S4, because it's 4 rectangles, is delta x divided by 3. And now we have 1 times x0, so that's square root of 2, plus 4 times square root of 3, plus 2 times square root of 4, plus 4 times square root of 5, plus single root 6. So you see your pattern of 1, 4, 2, 4, 1. Yes.
This might be a dumb question, but is this only, like, can you only use this on parabolas, or is it any?
No, any problem. I said parabolas will give you the exact answer.
Oh.
Parabolas are the only one that will give you exact answer for
Okay.
Simpson. But you use this on any function. So if you have e to something, then these will not be square roots. It will be e to the 2 and e to the 3 and e to the 4 and so on.
Okay. The exponent just has to be even. That's
Mm-hmm.
okay.
So now we have 1/3 times square root of 2, square root of 2, plus 4 times square root of 3. 2 root 4 is just 4, so plus 4. Plus 4 root 5. And plus root 6. And that gives me 7.911, which is again that 7.9 that we are looking for. So we saw that all 3 rules gave us 7.9 for the same problem on the same interval, which is what they were supposed to do. We also used Calculus2s method to come up with 7.3, which was not as good, right? And if you're really interested at the somewhat exact answer or more precise answer, you will just integrate square root of x 2 to 6 as a decimal. So for our problems, exact answer here was integral of square root of x dx from 2 to 6, right? And it will actually give you the roots in the answer. So you will have x to the 3 halves divided by 3 halves computed from 2 to 6, which is 2/3 of square root of 6 cubed minus square root of 2 cubed. And that's the exact answer, right? But again, this particular function was easy to integrate, and you can compute this value if you care. But again, as soon as you compute square root of 6 and square root of 2, which are both irrational, you are immediately going to start approximating. So that's the exact answer. You cannot do better than that. That's it, right? So that's all you can do. And if you approximate this to get the decimal, well, then any of the other methods where you didn't have to integrate were viable as well, right? Plus, the whole point of the section is to use this whenever integration is not possible at all. And that is one of the goals. Now, there are other methods to be used as well, right? This is not the only thing. But that's the one in 8.8 called numerical integration. As long as you can plug in a value in a function and compute, right? You don't have to integrate if you have definite integral. Oh, by the way, the whole section obviously is only for definite integrals, because you have to have the 2 to 6 so that you can have 2 to 6 here for delta x and do the partitioning. Otherwise, you don't know where the numbers are. Now, for the exam, I usually say, there are 1 or 2 problems. If it's a 1 problem, I say use trapezoid or Simpson, let's say, to solve this particular problem. Or I have a problem that is asking you to use a particular one. Or I have a problem, state the 3 numerical formulas, right? Where you just have to write the 3 clouds, right, in this. So it could be 1 calculation problem. It could be 1 calculation plus write 3 formulas, or it can be 2 calculation problems on the test, depending on which way the test goes. Which, by the way, we should talk about the next test, because we'll be done with the material for the second test today. Bye.